Hello, everyone. Welcome to another Outreach live stream. This is John McNally, joined by Noah Chartoff.
Hello.
So today we're going to be talking about starting points and demonstrations in Wolfram Alpha Notebook Edition. Noah's going to be talking about a little bit of an introduction to those. I'm going to show an example of using that in a physics classroom. Noah's going to jump back and talk about a little bit of math application, and then I'll do a chemistry example. And also, if you have any questions, feel free to put them in the chat and we'll be happy to answer those somewhat as we go. And also toward the end, we'll definitely leave time for that. So great to see everybody. And with that, I will hand it off to Noah.
Well, hey, today we are talking, like John said, about Wolfram Alpha Notebook Edition. Those of you who saw our last live stream might recognize these starting examples, but for those of you who don't, I just like to use these to showcase what Wolfram Alpha Notebook Edition is like. Wolfram Alpha Notebook Edition, as you might know, combines the flexibility and user-friendliness of Wolfram Alpha with the power and workflow of Mathematica. Like, as these examples show, the default sort of cell in Wolfram Alpha Notebook Edition, like if I just start typing 3 + 5 with no other sort of prompt, will be a natural language cell, these orange cells. The example I did just here is purely mathematical, but you can also use natural language, English, the way that you would say what you want to mathematically do. Like, consider these 3 examples. All of them define functions. Let f of x equals something, set g to something, define all those things would read as defining functions to a human, but there's no syntactic consistency here. Still, the program understands. When you run these cells, it translates the natural language you use into Wolfram language code. Notice that all 3 of these code examples have the same sequence: underscores next to the x's, colon next to the equals. All of these things are important in the code language. But in natural language, you can use brackets or parentheses. You can say the word equals, type equals. There's a whole lot of flexibility. And unlike in Wolfram Alpha, where everything you do eliminates the previous thing you did, you can use these definitions to define a 4th function. You can then graph that function, see what you get. Little fun example there. And I absolutely love all of this flexibility. But when you're working with a computer, you want flexibility, but you also want reliability. You want to know that you can predict what code will have what results. Now, Wolfram is great at teaching what its code does, especially through reference.wolfram.com. I love this. A huge collection of all sorts of built-in functions for the Wolfram language. Like, as an example here, list plot. I can click on this, and the first thing it does is it tells me the various ways I can enter parameters into this function and what those will do. You know, I can enter a series of points, series of 2D points, and then it will make a scatter plot of those points. I can enter just a whole bunch of points, just a whole bunch of numbers in a single set of brackets, as curly brackets, as opposed to all of these paired, each in their own curly brackets, and it'll create a plot where the x coordinate is 1, 2, 3, 4, and the y coordinate is whatever those numbers are. And then it shows me examples of code and what that code will do. All sorts of examples, starting from very simple ones and going to more and more complicated ones as it goes on. I love that sort of interface. By the way, this is also built into Wolfram Alpha Notebook Edition and Mathematica and other Wolfram products. Like, let's take a look at manipulate as an example. This piece of code uses manipulate to create a dynamic output that can change as you move the slider. And if I click on the little wolf head here and select manipulate, and you might not be able to see, you see the little I next to manipulate there? If I click on it, it gives me a version of these instructions for how I could insert parameters into manipulate. John, you see everything I'm doing here?
Yep.
Great. And unlike the online version, all of this code is live. You know, I could write in, I could say, add +7 to these instructions and move the graph up a bit. And just see what happens, explore, experiment. So you might be wondering, okay, that is how I get instructions on how to use the Wolfram language, the coding language that we have. But what about examples of how to use natural language, like this stuff in these orange cells? Where do I find out about that? Well, one of my favorite places to go for that is to starting points. See this orange ribbon up here? And by the way, if you're on an online version of Wolfram Alpha Notebook Edition, you will not see this orange ribbon. It isn't there yet. I've been told it's weeks away, but this will be something that you will want to check out on the desktop version. Also wanted to stress, we're going to be uploading a version of the documents that we're working in here. So if I'm ever scrolling too fast for you to read everything, you will get more of a chance to go through that at your leisure later. But this orange ribbon has a lot of great pre-made functionality. And the one I'm talking about now is called starting points. I can click on topics that I'm interested in, and I will find a huge amount of natural language prompts on that topic, showing me what I could do. I'm going to go to univariate plots here. I happen to like that one. Like the reference documentation for the Wolfram language, this usually starts off simple and then gets complicated as it goes. In this example, we're looking at plots of functions of a single variable. And it starts off stressing the flexibility of this language. Plot x² - 4x, then graph all these things. Notice the translation when you said graph was a function called plot because they understood what you were trying to do. Draw also understood what you were doing. A lot of flexibility here. But you might also notice, and I'm scanning through quickly here, that then it starts saying plot, plot, plot. A little bit of graph here, plot. And that's because it's telling you that plot is a very reliable term for graphing a lot of things in natural language. That's something I like about these starting points, that they can give you trends in the natural language, things that can help you sort of find your feet. Excuse me. It also throws in interactions with other Wolfram functions than just the ones used to graph. Like I like this one. It uses table, which is a great way in the Wolfram language to not just create one thing, but create several things at the same time with parameters that tell you how many to make and what to keep track of. Like here we have sine n of x plus cosine n plus 1 times x, not of x, times x, for n going from 0 to 6. You see when it runs that code, you get the full 7 outputs of all of those different things for each integer value 0 to 6. And then you can say plot that, plot all of those, and you get, I can't help but enjoy that. That's pretty. And just like in the reference documentation, this code is live. I can say, all right, let's not just do 0 to 6. Let's have n change from 0 to 10, and then throws a whole bunch of other terms in. And when I say plot that, this already twisty, turny thing turns into, oh my goodness, a lot of fun. So plenty of things to explore in here. Want to go down to another example a little bit further down. I want to stress, by the way, the things in starting point are not examples that John and I wrote for this presentation. They're built in. Everyone who gets Wolfram Alpha Notebook Edition gets this in all of these documents, all these examples built in to their experience. Give me just a second. I'm going to go down here to define a recursive sequence. Like I said, it gives examples of functions that are built into the Wolfram language. Also shows you how you could create some of your own. Like here's a recursive sequence that is defined in this document where a of n is equal to a of n minus 1 plus a of n minus 2 divided by 2. Okay, so it's like the Fibonacci sequence, except it's the next term is going to be the average of the previous two terms. And the first two terms, as opposed to the Fibonacci sequence where they're 1 and 1 or 0 and 1, depending on how you look at it, the first two terms are 1 and negative 1. And then you can, it uses that table functionality that I mentioned before to show you a bunch of those terms. The average of 1 and negative 1 is 0. The average of negative 1 and 0 is negative 1/2. The average of 0 and negative 1/2 is negative 1/4, and so on and so forth, like that, then plots all of it as it goes. So can show you examples of how you could build your own things. Speaking of which, that's one of my favorite things to do with these starting points. See, the way that this document is structured into different topics and subtopics and all that, it's not just great to keep your materials organized, it's functional too. See, I can select just a single cell of this, or a cell and that cell's output, or the entire subsection by clicking on these brackets. And then I'm going to use my keyboard to copy. And I'm going to just open up a new document, which I'll now share instead. There it is, a new blank document. I'm doing this because I know how intimidating a blank document can be. And that's the default way that you see a new document in Wolfram Alpha Notebook Edition. Having to fill this space with structure that's formatted in a way that makes it make sense and allows you to interact with it can be some work. But right now, I can click on a space with no cell in it and just hit Control V on my Windows machine to paste in exactly what I had from before. Every single thing that's in this subsection is now part of this document. And I can run this code or change it around, like let's change the second term to 3 instead of negative 1. See how that changes the whole sequence? Yeah, it's no longer negative. The terms that used to be trending down into the negative space now are graphed up here, all that jazz. And I can also just select all of this code in this section and hit Shift and Enter and run it all in sequence. This can be really important if you have something near the end of your document that isn't working. Sometimes there's a single cell somewhere in the document that didn't get activated. So that sort of a command can help a lot. Not to mention the fact, and I'm going back for a moment here to the, excuse me, to the starting point, just to copy another set of those examples. I'm going to paste it above here. Wanted to do that in particular to note that these subsection cells, they help to segment the entire document. Look at that. when I clicked on this bracket attached to the subsection cell, it selected everything up until the next subsection. So if there's code that doesn't play well with each other, you can separate them by subsections and then not have to worry about running them on top of each other or having them interact badly. Instead, you can just run every piece of code in an individual subsection and not the one after it. I like that sort of thing. And of course, all of this is editable. So now we have a whole lot of code that's in an organized, easy to read way with text that you can use to explain the code below if you spell it correctly. And you can add in new things like bullet points. You get that by typing in an asterisk is the first thing that you type, like Shift 8 on a Windows computer. Bullet points to talk about individual sections of all of this. It's something that can be a big help when you're creating a lesson, to just have everything structured in that sort of a way to begin with. Let me close this real quickly and share a different screen. Going back to the original document. By the way, if you want to get rid of this starting points interface, just click on starting points again. But instead, I'm going to go back because there's something else I want to show you that I personally like. Excuse me. Have polynomial equations. I'd recommend checking out as many of these as you're interested in, but there was something at the very end of the polynomial equations starting point that I also liked. Now keep in mind, all of these examples, natural language, they're written by developers at Wolfram. They wrote them to be good introductions to the way that natural language works and a good sense of the scope of the sort of things that you can do with it. This, on the other hand, is a demonstration, which means it wasn't actually created by people at Wolfram necessarily. It was created by someone in the Wolfram community, maybe a teacher, maybe a graduate student, but someone who wanted to create this for probably their own purposes to demonstrate something. And then they shared it with other people so that they can use it. Look at this example of polynomial equations, something where they give the long equation that'll help you find the zeros, and then sliders that will let you change the equation. Look at this part of the equation that says x plus 2.4. As I change this slider, both the equation and the graph change. And you'll notice that the term in this equation moves around so that all of the zeros as written in the equation are in order. I like that. Personally, I don't know how to actually make that happen. That's something I don't know how to code. But the person who did this does know. You can click on the orange arrows to find out more about who coded it. You can see in this particular case, it was Ed Pegg Jr., who did, I think, real nice work. You can download the source code from here, or you can go just to a web browser, like this one that's currently on Wolfram reference documents, and go to, just search for Wolfram demonstrations. I am indeed not a robot. And see a whole collection of them there that you can then browse through, take a look at, select them, and either download a working version of just the output, the working demonstration, or what I usually do, go to source and download the actual code and the output so you can see how they made it, maybe figure out how to make something like this yourself. Not only can you find this online, you can also find it in Wolfram Alpha Notebook Edition. Right on this same orange ribbon, right next to starting points, is demonstrations, where it will give you all sorts of categories that you can look through and explore demonstrations tied to all sorts of topics. I'm going to go now into a particular example or two of demonstrations that I like. Here we go. So this first one's a demonstration about the Monty Hall problem. Not sure if you've heard about this, but it's a famous problem in probability, originally debuted in a magazine. Someone wrote it up and said, okay, imagine a game show where there's 3 doors, and behind one of the doors is a prize. You don't know which one. On this particular example, it's marked, but in the game, it's a secret. And the contestant, you, picks a door. In this case, it was door number 2. You can see if I hit randomize here, the door that you pick and the prize randomly switch around. You pick a door that you think the prize is behind. Let's say the prize is a new car. And you know that behind the other 2 doors that don't have the prize is nothing, or a can of beans, a gag prize. Now here's the interesting part. After you've picked your door, the host, who knows where the card secretly is, will say, okay, now I know where the prize is, and here's what I'm going to do. I'm going to open one of the 2 doors you didn't pick. I know there's nothing behind that door, and they do. That's the blue arrow here. That's the door that they open. And then they say, okay, now there's 2 doors left. Do you want to switch to the door you didn't choose in the first place, or stick with your first choice? And the question was, and of course, you might have been right the first time, or you might not. And the question was, is either strategy particularly better, or does it not make any sort of difference? Now, they posted the answer, which was, it makes a difference. You want to be switching. You got a 2/3 chance of winning if you switch and a 1/3 chance if you stay. And when they posted that answer, the community went nuts. There were PhDs in probability and statistics writing in saying, that is obviously wrong. There are 2 doors left. Come on, it's a coin toss. What sort of difference could it make? And this debate went all over the place, because no matter how well someone explained that, well, you have a 1/3 chance of picking it in the first place, and that hasn't changed, and they're basically letting you open both other doors in this scenario. Oh, a lot of people were unconvinced. I heard the explanations. I was a little unconvinced until I saw someone actually model it using a lot more code than I recognize. Someone has modeled this game in a way that lets them then run 100 different iterations of it. And you can see early on, it may not be very obvious which strategy is better, but you can run up to 100 games with this and then randomize all 100 of those games and see how it changes the outcomes. But yeah, there does seem to be a difference, doesn't there? And by the way, after looking at this code for about 15 minutes, a lot of which I didn't understand, I caught up with some of the code enough to realize, okay, that part of the code is what's creating this number here. And then I made a version of it that would run 100,000 games as opposed to just 100. And set it running, and yeah, there it is. About 2/3 of those games are won if you switch. I love that, by the way. Here we got more experience with this game than we could have in a lifetime of playing it in just a couple of seconds. There's other examples of the of demonstrations that I don't alter at all. I just like as they are. Here's code from 2011, originally written in Mathematica, which runs great in Wolfram Alpha Notebook Edition, because at Wolfram, we stand by the backwards compatibility of the Wolfram language. And this one, I could probably alter it like I altered the other one, but I just like it, so I keep it as is. The demonstration project is absolutely full of all of these great little single examples that you could put into lectures, into assigned readings or homeworks, and the starting points is full of great structured examples of the natural language that you can use to do pretty darn near anything. Now, most of the examples I've been showing here are pure mathematics, or ones where it's not particularly clear exactly what we're modeling, other than that Monty Hall example. But there's plenty of examples that are going into boots on the ground, real world science too. So for that, I'm going to hand this over to John, who's going to talk about some of the other fields that starting points, demonstrations, and also just general use of Wolfram Alpha Notebook Edition can give you.
Yeah, so excuse me. As Noah was saying, the starting points and demonstrations are a great way to inspire you if you're trying to create content on the fly, right? Now, you can ideally, sit down for a little while, plan out an instructional sequence that's, going to take weeks or months to teach, and sort of create all that content once and then teach it. But as we all know, sometimes there might be a surprise snow day. Sometimes there might be a surprise global pandemic. Things happen in schools. What you were planning on doing in a laboratory setting in your, let's say, science classroom, maybe suddenly you need a simulation, right? So what you could do in such a situation, for example, you could go up here to demonstrations, and you could say, oh boy, so I'm teaching let's say there was a snow day or something that we weren't expecting, and I had my laboratory all set up, and I said, oh boy, and now I need a physics demonstration. So if I'm teaching high school physics, if we go here, we see that there's a lot of nice examples. And so we can click through and look for some of these. But let's say that we also have like a specific thing. So high school physics are ones that are, sort of definitely appropriate for that grade level and background knowledge. But depending on what your course is, there might be other interesting ones that are in, say, mechanics, or if your students are doing some really exciting stuff, you might even be interested in some of the particle physics ones or quantum physics ones. But we can click through all these different areas and sort of browse around and see what's there. So, I spent some time browsing around before getting on the stream today. And let's say that we know of a particularly cool one that we want to show. So what I'm going to do is close this nice browser for a second, and then you should still be able to see. So now here's my notebook. Let's say I know the name of a particular demonstration. Let's say that what I was planning on doing in my classroom was an example of Galileo's inclined plane experiment, and I want a demonstration of that. So if I happen to know the name of a demonstration that I've gone and found, either through the demonstrations project webpage or through clicking around in here, and I just type this in natural language, sure enough, I get something that will link me nice and easily to the demonstration notebook. So let's say, this is one of my all-time favorite experiments to do in the classroom, by the way. But let's say that we were wanting to do this experiment originally, and then suddenly I have to teach remotely. My laboratory is not going to be filled with students on the day that I was going to teach this. And so what can I do? I have a simulation now of a version of this experiment. So in this demonstration notebook, which is opened, we see that this was in fact contributed by someone in the Wolfram community. And by the way, if you have any good ideas for demonstrations, please code them up and put them in Wolfram community, because they're great. But here's something that you might not know that you could do with these. So when they're in a demonstration notebook like this, I could just give this demonstration notebook to my students. But the other thing I could do, I could copy this right here from the demonstration notebook. Now, let me close the demonstration notebook. And now let me, so this is my Wolfram Alpha Mode notebook that I'm using to create sort of a lesson outline that then I'm going to polish into what I'm going to give to my students on this surprise remote day that it turns out is happening and we weren't necessarily expecting. So what I can do is I can put in, let's say I want to make an output cell. And then I can just put in that demonstration from the demonstration notebook right there. and I can play this simulation. And so now, even though I was originally maybe going to do this with an actual ball rolling down a ramp in my classroom, I can now also engage with a simulation of this, right? Oftentimes having a sort of physical version of an experiment in a simulated version of the experiment lets students engage in different ways with it and is nice just in general. In my sort of hypothetical situation that I was talking about, I've been framing it as, oh, I didn't know I was going to have to teach remotely, so now I'm doing a simulation. But really, they're nice to just do together anyway. So at any rate, here's a nice inclusion of a simulation. So now, excuse me, what can we do with this? Well, one thing that you can do, if you remember, you can add sections and subsections, as Noah was talking about, to help structure the flow of your notebook. So let's say that after I let my students interact with this demonstration for a little while so that they kind of get a sense for what's happening, maybe now I want to include some discussion questions. Now, I thought about a little bit what sort of discussion questions I might want to do for this particular demonstration. So to spare you my having to type all of these live, here's some discussion questions that I thought might pair nicely with this demonstration. So for example, as our students are interacting with something, and again, many of the demonstrations share this quality where it's very easy to go back and forth. There's nice graphical and numerical representations of what's happening. There's color involved, a nice multisensory way of sort of trying to see what phenomena you're simulating, right? So given all that, what patterns are my students noticing in these numbers? And I can put in another text cell. Notice I've used the syntax for like a comment in Wolfram language syntax. I don't have to do that, of course, but I like to sometimes include this to prime students as they're learning Wolfram language syntax that, oh, when I see something like this with the parenthesis and then star and then close with another parenthesis star, that means that it's not going to run as code, right? This is sort of a comment. And so, I want my students to answer their things here. There's many different ways that you could tell your students where you want them to answer. And then they could just, when you give them the notebook, they could say, my answer is a good one, or whatever it happens to be, right? So this is, again, just from looking at the demonstrations, we can get inspiration for what we want to do in our classroom and connect it with the learning goals that we already had in mind. So what else can we do with something like this? Well, let's say that after our remote day is over, so our students have gotten a chance to interface with the simulation, and they've picked up on the detail that these are square numbers that we're seeing in the simulation. You might say, well, wait a minute, am I going to get perfectly square numbers when I'm doing this at some random angle, and I'm measuring in some unit that isn't necessarily going to give me these nice things? Well, no, our real data might be a little bit more messy than what we got in this sort of clean simulation. So what can we do? We could add another section where after our students are interfacing with a simulation, we can bring in real data from the lab that whenever we get a chance to run in our classroom, we do, right? Now, if I were going to do this in a teaching setting, I would import data either using import, so that's one way to do it, or I could have students manually enter data. There's a lot of different ways to accomplish it, but whatever you prefer for your particular goal that you have in mind. But I don't have students today, so for the sake of continuing the example, what I'm going to do is I'm going to generate some data. So let me just generate some quick example data here. So this is, of course, not going to be real data. And I'm going to type this in using Wolfram language syntax, just because for me, this is probably a little bit faster. But if we are doing this, so I'll just explain what I'm doing right here. So what I'm doing is I'm joining our 0, 0 data point, because when I first start measuring on this ramp, it's going to be, no time elapsed, and it's not going to have moved yet. So we'll join that data point. And then let me make a table real quickly. So in this table, so let's just say that we have some thing that comes from an arbitrary angle. We have something which is sort of physicsy related. And again, don't worry, I'm just generating some sample data here. This is not a critically important part of a detail for you to remember, right? And then I'm just going to use the random real function to sort of introduce some noise, because when my students are getting that data from their actual experiments, of course, we're not going to have perfect measurement precision. And so in this table that Noah mentioned is a good way to generate lists of things. I can also put in, let's say I want to do, whoops, and I've made a error here. I want to include my time and then how far I'm measuring after some amount of time has elapsed. And so where do I want to make my table? Let's say I want to start generating my fake data at a half second, go to 4 seconds, and do it every 5 seconds. So in this context, if I run this now, we're going to get some example data. So again, if you did this with an actual experiment in your class, you need to run any code in order to get some sample data. I just wanted to show that this is a really nice way that you can make sort of simulated sample data that has some randomness in it from hypothetical measurement errors that then you could have your students analyze in some situation where maybe your lab isn't available to you at the moment. A water pipe broke in the ceiling, let's say, right? And suddenly the lab area is flooded and you need the data to carry on with what you're doing. Of course, you can generate it using a computer, and that's one of the nice things. So, okay, so now that let's get on with the example here. So we've got this example data. So using natural language, and Noah will talk a little bit about how you might happen to know that you can do this with a natural language. But once we have this example data, let's say I want to do a list plot of example data. Right? So once I've got data in here, I can make a nice list plot of it. And I can even come down here to the suggestions bar. And let's say I want to make some labels for these. So let's say I want to do my plot of sample data. Let's say I want to have my x-axis be time, and then the y distance be some other measurement. I haven't specified exactly what it is that we're measuring in this experiment. Not critical for our purposes today. You would have specific instructions for your students, of course. And then by using these sort of drop downs, we're able to get a nice labeled thing. And I found some nice documentation on how to do this, as Noah was mentioning, in a starting point, right? So if you didn't know that you could do this, by browsing around in the starting points, you can see lots of cool examples of stuff exactly like this, where we start with some relatively simple natural language input, and then using suggestions bars and things like that, we can get some fancier options that make it into a nice looking plot. Okay, so what else can we do besides just making a list plot? Let's say that we want to go over with our students the concept of fitting our data to some sort of mathematical thing, right? But before I go into that, actually, let me not forget. So we can drop in more discussion questions, right? So after I've put in these plots, either having my students do it or showing them how to do it, depending on where they are in their learning of some of this functionality, I can put in more discussion questions. So what patterns do they notice in this data, right? So in the real data, they're probably not going to see these nice square numbers that were coming up before, but many of them should probably notice that there's a similar sort of thing going on, even though the numbers are not nice and square. If you were paying attention when I was making my sample data, you can see why, but here's this. So, okay, so let's say now after that they've thought about what are the patterns that you're noticing, what was different between the simulation and your experiment, and then what do you think causes these differences? After your students have had a chance to engage with this, we can talk about sort of modeling more concretely. So let's say that we want to fit the example data to some curve. Now, if I just say that, I see that I get a nice linear fit. And if my students are just looking at sort of r squared or just r squared values, they might say, yeah, okay, pretty good, right? I mean, it seems to be near these points. But we can see visually, and this is why it's also really important to not just look at sort of calculated statistics, but also sort of visualize what's going on with data. We can see both in the plot and in this nice plot of the residuals that, again, all of this came just from saying fit my data, please, in natural language. My students can see, yeah, there's a pattern going on here with these residuals. There's a pattern going on here. So even though, sure, the line goes kind of close to all these points, this might not be the best way of fitting my data to some mathematical object. And again, I can put in lots of nice discussion questions related to this concept. So again, I've thought about this a little bit beforehand. So let me just put in these. And again, as Noah said, after the stream, we'll tidy up some of our inputs and make available to you, notebooks on the community and linked in the description on this stream's permanent home, where you can sort of see all these as sort of a nice example of using starting points to help build curriculum materials that are really engaging for your students. So, okay, so where did we leave off? We had a fit of the example data. Well, maybe the students have realized, I actually don't want to try to fit this to a line. I want to try fitting it to something else. So right in natural language, they can say fit example data to a quadratic. Excuse me. And sure enough, we get a quadratic polynomial fit to our example data. Now, one of the nice things about Wolfram Alpha Notebook Edition, excuse me one second. One of the nice things about Wolfram Alpha Notebook Edition is that we get polynomial fits. If we change this to quadratic, we can see that this part of the code is different, right? So if we have a linear fit where we just ask it to fit the thing, we can see that in this Wolfram language syntax, this is a function, which is taking example data as the first argument, our variable is the next argument, and then by default, we're fitting a line. If instead we look at the output that we get here, we see that, yeah, I can fit to other sorts of polynomials. And this provides a great way for my students to interface with Wolfram language syntax, as well as just nicely being able to see, okay, now the residuals are not following any particular pattern here. We're getting a very nice fit that is better than our original one. Okay, so after getting into this with fits, I'm going to toss it back to Noah so that he can talk about how did I know that I could do all this nice stuff in natural language? So he's going to talk about fitting and that starting point.
Yep, because I think, John, I'm very glad that you showcased how easy it is to build all of this from the ground up, that it doesn't take a lot of typing to create some very useful and explorable materials. But also, we could look at examples of that in the fits starting point, that if you ever wanted to see more examples of all of this, and these are the sort of examples that inspired us to make a lot of this presentation, you could just go scroll through it one of these days, maybe edit some of this, see what comes up and see what you like, because there's an awful lot of materials at your fingertips. I also wanted to address a question quickly, which came up in the chat. Someone was asking about Bell's inequality. And I don't know enough about quantum physics to know the details of all of that, but I did want to address quickly that we're showcasing mostly natural language stuff here, because that's the default sort of setting that Wolfram Alpha Notebook Edition operates in. But like we showed you a couple weeks ago, if you click on the plus sign after clicking somewhere there isn't a cell and select other style of text, in my case, input was there already, but it's worth noting it's not one of the things listed on the drag down menu. So if you don't see it, just type input in. You will be able to create a cell that can accept normal Wolfram language code, which could allow you to do things like install the new quantum packlet, which is a very powerful thing that gives you a whole lot of tools to work with the Wolfram quantum framework, can take a look at quantum circuits, create a basis. I got to this by looking up Bell.
Also, it's good to note that there is a study group ongoing about the new quantum framework, and you can find recordings of past study groups on Wolfram U.
So the short version of what I wanted to stress is that although a lot of what we are showcasing here are things that especially work in Wolfram Alpha Notebook Edition, a lot of things that work in Mathematica will work here too. It doesn't have to be high school sorts of examples, undergraduate sorts of examples of materials. There's a lot of graduate level work that you can be doing in this program. So John, I'm going to throw it back to you now to move on to the other things you wanted to show us.
Sure. So the other thing that we can do besides this physics example, let's say that I also have a chemistry class. Let me throw in a chemistry example. So chemistry starting point.
I can't see what you're doing right now.
Oh, excuse me. My screen was not shared. Let me fix that. Thank you. Okay, yeah. So now, so what I did was I took my notebook that has this other example in it, and I just went here to add a section. And I said, now let's explore a chemistry starting point. So again, if I want to explore these nice starting points, the ribbon up here, I've got demonstrations, starting points, and we're not talking too much about them today, but these interactive plot quizzes are also great. So definitely check those out when you get a chance. So if I go to starting points and I go to chemistry, let's say that I'm teaching about reactions. I have a friend who has this great unit that he likes to teach that involves the concept of limiting reactants using a reaction between vinegar and baking soda, also known as acetic acid and sodium bicarbonate, right? So let's say that I'm not sure what is the chemistry functionality that I can access with Wolfram Alpha Notebook Edition. Maybe I haven't played around with it before. So if I go to the starting point, I see the first thing, oh, I can look up reactions. So then that might give me the idea. Let's say if I go back to my notebook that I'm sort of generating some lesson content in here on the fly, let's say that I want to find the reaction that is what I get. Excuse me. Oh my goodness. So let's say that I want to explore the reaction that I get when, in fact, let me not even put in reaction. Let me just say acetic acid plus sodium bicarbonate. And if I just type in this in natural language, the default thing that I'm going to get without even using full Wolfram Alpha results is, sure enough, this reaction. Now, I did this, if I remind you, because I was browsing around in this nice chemical reaction starting point, and I saw, oh, this is a thing that I can do. And now what I might do is I might say, okay, so in my classroom, I'll say to my students, let's say that I mix acetic acid and sodium bicarbonate. Can you predict what the reactants are going to be based off of your current knowledge of chemistry? Depending on how far into your chemistry education your students are, this might be a difficult task, this might be an easy task. It all depends on what your learning goals are and what grade level that you're dealing with. But after giving your students a chance to predict this, you can verify using this nice, easy computation. So then, if I go back to my chemical reaction starting point, and again, we didn't make these. These are part of the ribbon up here, which are created, well, I should say we didn't make these on the fly. These are created as part of Wolfram Alpha Notebook Edition by the developers here at Wolfram. And so if you look further down, so that was just the first one, gave me some inspiration. Oh, I can even balance these reactions. Well, that's interesting. What happens if I go back to my presentation notebook that I was, experimenting around with this chemistry functionality? Let's say I'm learning how to use some of this functionality myself as an instructor. So if I want to put in, let's say we're looking for something like this. Oops. Let's say that we're looking for something like this. I want to balance acetic acid and sodium bicarbonate goes to this reaction. So my students or I can get a nice balanced chemical reaction that comes just from words. Now, in this particular one that I'm showing, that's the vinegar and baking soda, it's pretty easy to balance. But as I can see from my chemical reaction starting point notebook, it doesn't necessarily need to be one where all the coefficients in the reaction are one. It can be, as complicated a reaction as you like. So we also see from the starting point notebook, oh, there's show steps functionality for how to balance these reactions. So there's various ways that you can use this. You can use this either as a way to help your students engage with the laboratory experience and do something with their measurements before you formally teach how to do stoichiometry and balancing reactions. Or you can use show steps as a learning tool to help them check their work when you're teaching that as a learning goal. It really depends on what your learning goals are. There's a lot of advantages to letting students engage with the hands-on experimentation and simulation, and as a first step, have some of the balancing and things like that done in an automated way, and then later return to those concepts in more detail if you want to as part of your instructional sequence. Or you might be teaching an advanced course where showing these steps are just a way to check your work and gain confidence that, yes, I know how this works and I can do it myself if I had to. But if I have this ability to do it automatically, I can just do that too. So let's return to making this little short chemistry lesson here. So, all right, I didn't know that these functions existed. Let's say, if you're familiar with the chemistry functionality of Wolfram language, you'll know that there's a lot of really cool chemistry functionality. But if you're new, maybe you didn't know. So, all right, I can do these things. What other kinds of stuff are in this starting point? Let me go back to the starting point. We see that we can get ionic reactions that are happening in solution. I can do all sorts of interesting things related to that. Maybe that's not my learning goal for this lesson, but I get to the stoichiometry section. I see that, like many chemistry teachers, maybe I don't want to spend 3 full weeks, teaching the mathematics of stoichiometry before I can use it in my lab. Maybe I want to engage my students with the laboratory experience and then return to some of the mathematical details. It turns out this is a great tool for doing that. So, okay, let's go back to my example of acetic acid and sodium bicarbonate. So I saw, if I go back to my, so you should be able to see the starting point notebook now. We see that, oh, how did I get that? I said stoichiometry, and then I put in some of my reaction, and then I put in some information about measurements, and then I got this nice output. I also see I can show steps for this. So if I go and then in my presentation notebook, which you should be able to see again, if I, wrong kind of cell. There we go. If I say stoichiometry, just in natural language, I don't even necessarily have to type in the full chemical formulas for these. Let's just see what I get. Sure enough, I get a nice stoichiometry problem solved, which if I wanted to, I could show steps for. If I'm, again, as an instructor experimenting to see what the functionality is, I see this theoretical yield. And then I might say, oh yeah, I was planning on teaching about the difference between theoretical and actual yields. I wonder if it can do that too. Well, let's go back to the starting point and let's see. So if I keep scrolling in my chemical reaction starting point, I see these stoichiometry examples, lots of really good ones. And sure enough, there's one that talks about computing the percent yield. Aha. So sure enough, we can do this in natural language. Of course, I have to type in the numbers of the measurement because that's a measurement that I took. But everything else, nothing mathy about this, nothing, computer code about this. This is a natural language input. So let's do this for our example that we've been sort of using of vinegar and baking soda. So now let's say that I want to go back to here. So, okay, so I've seen a nice way to get that. So I can say, excuse me. I can say, all right, let's say that I don't know how much acetic acid I'm going to use. And let's say instead that I'm going to get, I don't know, 1 gram of carbon dioxide out. Now what we see, if my students go and they measure by collecting some gas that forms when this reaction happens, okay, I only got 1 gram of carbon dioxide when I knew that I had this much sodium bicarbonate and extra acetic acid. We can see what the theoretical yield of carbon dioxide should have been if everything had totally reacted. But this was the percent yield that I got in my actual experiment that I ran. And so we can use this to sort of assemble a lot of interesting pieces into a nice way to frame a lesson about limiting reactants and all kinds of stuff. Now, the really nice thing about this is that we can use all this functionality to frame a laboratory experiment. So what I'm going to do now is I'm going to drop in, because we're running a little short on time. So this was something that I had thought about a little bit beforehand. So here's a lab design extension to assess our students' understanding when they get to play around with this functionality. So suppose that we needed to find the mass of a sample of sodium bicarbonate. And we tell our students it's definitely less than 5 grams, but all the lab equipment for directly weighing your sample was broken. So you can't just put it on a balance and see how much it weighs, but you want to know the mass. However, we do have a couple liters of vinegar, which we can tell them, what molarity and what chemical that vinegar is, in case maybe they didn't remember that part, or if they're advanced students, they can figure that out. So we've got some vinegar, and we've got all the necessary glassware to accurately measure the volume of solutions. So then, rather than spending 3 weeks teaching sort of the process of creating a chart like this, we can jump right into the engaging part. Critically think, design a laboratory procedure that can allow you to estimate the mass of the original sodium bicarbonate sample. So one way your student might do this to play around with these natural language capabilities before designing their experiment is they say, well, let's say, what would happen if I tried to react 5 grams of each of these? What would be the theoretical result? So the theoretical result is that the sodium bicarbonate would be our limiting reactant. And so your students could also play around, and through some trial and error, which again, in the full notebook, I'll show one sequence that they might take to be able to do that. But they might eventually reach the part where they say, okay, let's say that I mix 70 milliliters of this particular molarity acetic acid with some 5 gram sample of sodium bicarbonate. What would happen in that situation? And in that situation, we would get basically the same amount of each. And so there wouldn't really be a limiting reactant up to, measurement uncertainty and significant figures and all that good stuff. So then your student might think, okay, well, what happens if I, run this amount of acetic acid with an unknown amount of sodium bicarbonate, but I measure in my lab, I got that much carbon dioxide out. What would that tell me? And then we get all this great information. So that's how we can use, excuse me again, that's how we can use this functionality in order to, instead of just teaching some of the calculational details here, we can jump into using the calculational details right away to critically think about how I can go from some situation to making an experiment where I know what I'm adding here. I don't know what I'm adding here exactly, but I can measure this and then think about what happens and what that means. And that's really powerful. So since that's about an hour, we want to definitely make sure that we get a chance to answer any questions. So I know that Noah has been taking a little bit of a look at the chat. Are there any questions?
I saw a question that I hope what I showed on the fit starting point helped answer, which was, can we see a lot of different fits? I'm going to jump right back into that. John, can you see the starting point that I'm opening up here? That, yeah, there's, of course, linear, polynomial that can be a quadratic, or here somebody requested it be a quintic fit, a polynomial where the leading exponent was 5, and rightly so, because it looks like a pretty complicated set of data. Can go into trigonometric fits, can go exponential, logarithmic, all sorts of different ways of fitting these things to data. The exact question, I think, was, can you show us all kinds of fits? And of course, I understood what they meant was, can you show me a lot? But naturally, we're not showing everything that this program can do. We are scratching the surface, in the same sense that the Library of Congress scratches the surface of what mathematics can do. Everything that's ever written scratches the surface of what mathematics can do, because this is a very flexible and very powerful program. So there are an awful lot of things that it can do by design right from the get-go. There are an awful lot of things that you can build up in it to do that it couldn't do in the first place. So absolutely, starting points are a great way to do exactly what it says on the tin. Be starting points. They are a great way for you to get a sense of the sort of scope that you're working with. But as with pretty much everything else, the best way to find out about that is to try it, is to explore and see what you find. So I certainly encourage people to be doing that. The document that we'll be uploading will help, but keep in mind, most of what we showed you today is built into Wolfram Alpha Notebook Edition right when you open it. Starting points, demonstrations, you don't have to download anything extra or do anything extra to make that happen.
I also saw a really great question. Let me share my screen again real quick. Let me make sure I'm sharing the right thing. Okay, so the question that I saw in chat was, can we do multi-dimensional stuff with this? Maybe you were just talking about fits, in which case the answer is that, yes, you can fit things of more than one variable as well. But when I hear multi-dimensional stuff, one of my favorite things is vector calculus, because it's just pretty, right? You can get lots of cool, pretty pictures with vector calculus. And so because we have this nice vector plot 3D functionality in the Wolfram language, if I just type 3D vector plot of some vector field in natural language, sure enough, I get a nice 3D plot, right? And we can do all sorts of stuff like that as well. In fact, let me do, well, let's just do another one, right? Let's do a vector plot of maybe a slightly different vector field. Oh, I think I put in the wrong. There we go. So here's another vector field where we have another very interesting picture. So I don't know if vector calculus was what you were thinking of when you mentioned multidimensionality, but it's what leapt to mind when I heard that question. So I wanted to mention that, yes, you can do things like that with it as well.
Can I throw in another example here?
Yeah, please do.
So the examples we were just looking at are a great example of how, when you know some Wolfram language, you'll be able to query the sort of function that you want, and we'll get a helpful result. But I want to showcase something I created myself here. It's not in the starting points. Graph sine of a times x squared plus y squared varying a. That's all I wrote. So you can see what basically we're doing here is we're taking the sine of the horizontal distance a point is from the z-axis, and multiplying that by a, some number. And then in comes functions plot 3D and manipulate that I never wrote up here because it understands what I meant. It says, all right, I see that you want some sort of graphical depiction. You want to vary something. The thing that you are asking me to graphically depict has two variables, so I'm going to go for something three-dimensional. I want to vary something, so manipulate. And then since a higher a here will compress this function and make it change faster by moving a up in this three-dimensional example, I can see that exactly that happens. What previously was just sort of a hill now is starting to ripple a little bit. And I didn't tell it anything about what sort of constraints to put on A. So it just said, all right, A goes from 0 to 2, I guess. But I could have said it from 0 to 6, thrown that into the mix. And now it changed this little number right here to let this thing become even more of a ripple pattern as I increase A and make the whole thing more and more compressed into the space it's in. You can see it gradually changing. into something absolutely nuts right here. I show sometimes examples like this to teachers who are doing high school math, and they think, oh, this program may be way too powerful for what I'm working with. But keep in mind, the concepts here are things a high school math student could understand. Maybe you wouldn't want them typing out all of this code if you know they don't have a lot of experience with computers, but they don't need to. They don't need to. Natural language will let you say the sort of thing that you're looking for. Like a human being, every now and again, it'll say, wait, what? I'm not, could you say that a different way? I don't understand exactly what you're saying to me. So you may need to write it a couple of different ways before you get the result that you want. But for one thing, it's very, very good at figuring that out. So I would say that's not going to be the common experience. And for another thing, take a look in the starting points if you're curious for good examples of prompts, and maybe give that a whirl, give it as an example of something you want to try out.
Yep. And related to that point that Noah was making about instructors at a certain grade level being concerned, oh, is this too advanced for my grade level? I would say the answer to that question is never no, or is never that it is too advanced, right? The answer is that you should always keep in mind, what are your students going to be doing next after they leave the grade level that you're teaching, right? The sooner that you can introduce some of these really exciting concepts, the sooner your students can sort of latch on and say, yeah, I want to go study that, right? And a lot of these computational tools make the concepts much more accessible than they would be if you were teaching with pencil and paper, right?
Exactly. This is the whole idea of Wolfram Alpha Notebook Edition, is that math is a language. It's a language with its own subject matter that it tends to stick with, but it's a language with vocabulary, syntax, grammar, prose, poetry. It's a language that people communicate to each other with, and they do it in a whole lot of different ways. There are people who think about math primarily through just numbers, equations. There are ones who think about math through English sentences that describe numerical things. There are people who think about math, and I'm just going to show off one other nice little thing that's on this ribbon that I hadn't planned to show, but what the hey, it's just come up. There are people who think about math symbolically. And with this typesetting tool, also in the orange ribbon, you can click in on this and throw in a definite integral from 4 to 1,000, let's say, natural log of x dx. And some people might think, oh, that's neat. Yeah, it's a LaTeX thing, right? Yeah, absolutely. I'm glad that you can write in non-working examples of mathematical symbol. No, this works. If I hit enter on this thing, it's going to actually change that into code that then gives me a result. So the whole idea is, however you think about math, if it's a coding language, if it's symbolic, if it's in English sentences, whatever your way of thinking about math, we want to let you communicate and work through that way of thinking about it. And that's how this all works.
Yeah, and I would also emphasize that you don't necessarily always have to choose one mode of engagement. In fact, a lot of times you want to allow your students to engage in these topics in a lot of different ways. For example, at the very beginning, when I was talking about using a demonstration to simulate something instead of doing it in the lab, there's no reason you have to pick. You can do both, right? And that makes for a really nice learning experience for students, where they get the nice clean interface and clarity of a simulation. They also get the nice hands-on and fun experience of working in an experiment, with materials that they can sort of hold in their hands. If you mix these methods, they're very powerful, right? So you don't have to do everything on a keyboard. You can use computational tools when computational tools are the thing for the job. And you can use, a ball rolling down an incline when that's the tool for the job.
Just wanted to add, I know we're a little bit over time. Looks like we can go for just a bit more, but if there are any questions that we don't get a chance to get to in this presentation, we're going to be putting contact information for us on the notebook that we upload to the permanent YouTube version of this video. So you can download that notebook, reach out to us afterwards. We'll be around. So
yeah, so we'll see if there's any more questions.
Looks like nothing that isn't outside of the scope of what we're talking about.
Yeah. So like Noah said, please remember to comment any other questions if you happen to be watching this after the fact. If you know someone who might have a question, feel free to send it to them and they can comment. We would love to hear your thoughts about how you would want to use these tools, what questions you have about how you would want to use these tools. We definitely are here to answer any questions that you have, so please keep them coming. But I think that will be all that we have for the moment. So we'll look forward to hearing from those of you who are going to be watching this after the fact. So with that, thank you very much for joining us, and we will see you next time.